Begin Podfix Network transmission. In 3, 2, 1.
You're fly fishing in a stream, getting those ankles wet, or deep in the ocean, casting nets. Fish nerds. Fish nerds. Fish nerds. It's a podcast.
Hello and welcome to the Fish Nerds, a show about fish, fishing, and eating fish. I'm Clay Groves, Chief Executive Fish Nerd, Licensed Fishing Guide, your best friend. It's been a while since I put a podcast out, but Doc Martin said, I got some stuff we got to talk about. And I said, then I'm going to make a podcast. So tonight's guest is Doc Martin. Good afternoon, Doc.
Hey, how's it going?
Good. I miss you.
And you put out a bunch in November, though, right?
I did 30 in November.
So that's like a lot.
Yeah. So we've done almost 300 regular episodes, and over 500 total episodes with all the bonus content. So there's a lot of podcasts out there. And there's still so much more to do and say. So we're going to do a few more things today. You got hold of me because, first of all, you sent me an interview that you did with Dr. Rachel Bose?
Mm-hmm.
Dr. Bose about river food webs, which we're going to share on this week's episode. Mm-hmm. I also wanted to make sure I did get a shout out. John King, the crappie hippie, friend of ours. Everyone knows John King. Sent me.
He's wonderful.
He's a wonderful, crazy old coot. And he sent my kids and I a package of fly tying material. So we're going to learn how to tie some jigs up. Maybe we'll tie some up and mail them back to him because he loves tying jigs, and I thought it was really nice of him.
Oh, that's so exciting.
Yeah. But we're going to talk about microplastics. You've got a project you're working on, so I want to kind of lead with that.
Sure.
I am going to make you talk about fishing also, though, right after that. So,
good.
Yeah.
I'll do my best.
That's all right.
That's outside of my area of expertise.
But you know fish, and we're going to be talking about fish behavior, which might help a little bit with that fish.
Okay,
talk,
I do know some things about that.
Well, good. We're going to get into it, but let's get into the main reason we have to put a podcast out this week, because you messaged me and you were very excited.
I'm very excited. Yeah. So I don't know how late I messaged you, but I had an idea, and I'm like, I should just
4 in the morning, 3 in the morning, some ridiculous hour.
And so I think a lot of the listeners already know that in my aquatic ecology realm, I do a lot of research on microplastics, just their presence, what they're doing to the abiotic environment and the biotic environment. That's where we're focusing more recently. And then the other part of my research house is STEM education. So I do kind of two things. A lot of those times they are intertwined because I can't help myself. And so what I've been working on, we've made 2 cures, which are course-based undergraduate research experiences. And so, if you're
did you come up with the initialism before?
No. So this
okay, I want to call it cure, so we got to find the right words to match that, or did it just work out?
No. So actually, I didn't know cures existed, and I was doing these research projects with undergraduates because that just made so much sense to me. Like, that's why I fell in love with science and biology, because you could do it, you could see it applied, and you could get that feeling of, I'm doing something relevant, and it makes a lot of sense contextually. And so when I started to want to write up what I was doing, I came across cures, and I'm like, hey, that's the thing that I'm doing. And I should have looked at that first probably, because I was reinventing the wheel when it had already been there for such a long time.
Well, in education, we do that all the time. It's a normal right. Education practice. I got an idea, then you find out someone else did something very similar, and you start over again. So, yeah. And
so the cool thing is that a lot of cures are kind of either microbiology based. And so we've been releasing some ecology based cures. And so that's kind of the new part of this, is there's not a lot of those that are already out there. We focused on microplastics. We're focusing on students publishing their research. So it's kind of that next level of, yes, we're doing this undergraduate research experience, but it really is geared to being real, tangible science relevant to current scientific trends, which is pretty cool. So in that realm, I thought it would be really useful to broaden what we've already got going on, where we're getting a lot of undergraduate students at my university involved. And I thought, well, people are into this. I've gotten a lot of really positive responses, both from the scientific community and just community members in general, that they're interested about microplastics in their area. Where do they come from? Is this something that I need to be concerned about? And so I thought our listeners might be interested in doing research with me.
Well, why wouldn't they? They're a bunch of nerds. They love that stuff.
Right. And so I'm imagining that a lot of our listeners probably go fishing or, do outdoor kayaking, boating, swimming, whatever water recreation kind of stuff. And they might be curious, are there microplastics in the area where I go a lot of the time? And so if that's the case, if you're listening now and that sounds like you, like, I really would like to know this, then this is definitely an opportunity for you.
Oh, good. And microplastics is so trendy right now. I know our local thing up in New Hampshire here, we've got a group called Green Mountain Conservation. They're doing a big microplastic study in all the waters around here. And so it's a real popular trend right now. So it's probably getting funding and getting other people interested. It should be pretty easy, I think.
Yeah, I'd say that it's definitely trending now for citizens in the realm of sciences. It's not really considered cutting edge anymore. No.
Well, it takes a while for that to trickle down to our lizard brains here to get, so we can make it all work together. So
yeah, I think microplastics hit the scene in peer-reviewed science probably about 10 or 15 years ago. And now that we're getting a lot more information from the scientific community and a better understanding, of course, that's more easily translated now to people to say, hey, we actually know some things. There's a lot that we don't know. One of the things is a lot of the microplastic studies are done in marine systems. There's been a big push to change that. And so I know there's some places around Chicago, Oregon, up you in New England, but there hasn't been a lot of freshwater studies yet. And so, and maybe there's not one in your area, wherever you're listening from. And so that's what I want to do is I want to get just a bunch of samples from wherever they're coming from, just water samples. It's really easy to take, and then process those and combine that with some of the other work that I've already done. I don't know if we want to talk about that. It's a lot, and I have always a lot to say. Usually
right.
Too much.
Well, we can come back to it because I don't have a lot of time today. But yeah. So can we take a look at so let's pretend I am listener man. I'm listener man, and I want to participate in this citizen science project. What does the work look like for me? I connect with you somehow, and then what?
Yeah. So there's, I guess, depends on how you want to connect. I know the Fish Nerds has a hotline where they could probably leave a message and just say, leave your name and some way to contact you, so we can make sure that you get on that list.
Mm-hmm. You know what I can do, Doc, is I can create a Google form, and I could put a link in the show notes. And so in the show notes will be a Google form. Click on that link. We'll also put up on Facebook, and you fill in the blanks. You're going to give us your name, your email, where you're from, your address, and you fill in the blanks, and you'll be entered to be part of the fun.
Yeah, and we won't share your personal information with anybody.
Unless they pay really well.
No. And so what'll happen is I do have a grant for this. So I will... depending on how much money I have and how many people sign up, we might have to cut people. So, maybe a first come, first serve. So if this is something you want to do, man, get on there and sign up.
Mm-hmm.
And then I'll probably allow folks to sign up and through March 1st. So it'll give you about a month, a little bit over a month to get this podcast out. Go and sign up before I have to make the cutoff. And then what'll happen is you'll be contacted via the email address that you sent by me, Doc Martin. And I will make sure that, yes, you did intend to sign up. This is something you are interested in doing. And if that's the case, I'll verify that either if you did send me an address on the Google form, that's the address you want things sent to. If not, what address should it be?
Right.
Get all of that stuff ironed out. And then I will send you a sampling kit. And then you'll also get a link to a video tutorial where you get to watch me and some of my students do the sampling and tell you what all that equipment is, how to do it, and what to look for and pros and cons. It'll be, maybe 10, 15 minutes long. It should be pretty short. And then you'll take the kit. You'll go to your water body where I have to assume you have permission to be, right? So Don't just sneak places. Please do not do that. And then you'll take those samples following that procedure, and then I will have, you will not pay for shipping. So you will be able to ship it to me, and I will pay upon delivery. Those instructions will all be included when I send that package out to you.
Perfect.
And then once we start analyzing some data and things, your name will be in the acknowledgments.
Oh, it'll be famous.
A hard copy of the paper when it's published, which, don't hold your breath. It'll probably take a year or two for that to get done.
Well, that's pretty exciting. It's a pretty great project that people can get involved with. And so I was talking to someone around here at the local conservation people, and they're saying one of the biggest forms of microplastics in fresh water is from laundry and from your clothes, which have tons of plastic in them. And
textiles. Yeah,
textiles like the fleece. 30 years ago, we were all so proud of recycling those plastic bottles into fleece, and now look what we're doing. So you never know.
Yeah. Textiles, and then things like Tupperwares and water bottles are really, really big contributors to a lot of the microplastics pollution.
Yeah. It still baffles me that bottled water is so popular. I can't even understand it. Here's a bottle of nothing.
Some places you don't want to drink the water.
Well, in those places I understand, but most places the water's good, so you don't need
Most places the water's good. Although I live in a place where I think we're number 2 in most polluted water. So,
maybe
it depends on the kind of pollution, I guess I'll say. We are bad for lead, so that's kind of a big deal.
Oh, that's delicious if you like neurotoxins. All right, so that's good. So we'll put a link in the show notes. You can click that link. Fill the form out, and Doc will get back to you with how to participate. We'll report back on how this is going and updates, and we'll be pushing this out for a few episodes to make sure that people sign up so you can do it. And I'm going to put together a little prize package, too, so anyone who signs up will be entered to win a little prize package, maybe a Fish Nerd's hat, and if you're in New England, I'll take you fishing. So it'll be fun.
Ooh, that'd be pretty cool.
Yeah, you've been on my boat. Everyone loves going on a big boat. So
Heck yeah.
Heck yeah. All right. Thanks, Doc, for that. I do want to, because we only have a few minutes left, because we've got an interview here with Rachel Bowes, which takes a long time. And I want to make sure people have time to really listen to that and talk about river food webs and how they changed over time. It's very interesting. But before that, I just got back from South Carolina. I took a pandemic vacation. We did everything outside. We tested for COVID before we left, all that stuff. Wore N95 masks on the planes because we don't want COVID. But so don't hassle me about being COVID safe. We did that. We had to take a vacation. But I went fishing, and my friend COVID John, who, by the way, had COVID in his condo while he was telling me how to fish. I didn't want to fish with him, but my in-laws kind of pushed him on me, lent me some gear, which I sterilized and kept 25 feet away from him. I'm not joking. I call him.
Yeah, because you're a kind of a higher risk, right?
Yeah, I'm a higher risk. I do not want COVID. Anyway, guy's gear, and I watched him fish for a bit. He didn't have COVID; his son did, but it was in his house. And I watched him fish. And we were catching red drums. He was catching red drums using these fishing lures, catching dozens of them. And it was fun to watch, and I couldn't catch anything. And then my nephew, who's 11 years old and has a little bit of a speech impediment, I was asking, he was telling me he catches fish all the time down there. I said, we're in the Folly River in South Carolina, which is by Charleston. And he was saying, I said, how do you catch fish? And he goes, what do you mean, Uncle Clay? I put bait on my hook. I said, yeah, but what's your setup? Do you have a fluorocarbon leader, and you have a fancy hook, and what kind of weight do you have on there, and how's it tied on there? And he goes, I don't know what you're saying, Uncle Clay. I put shrimp on a hook. And so I kept pushing him. I said, yeah, but how's that hook tied on? What size hook is it? All this stuff. And he goes, Uncle Clay, I don't know what you're saying. I just put shrimp on a hook. So I stopped for a second, and I thought about the words he was saying, which was put shrimp on a hook. So I went and got a hook, and I put shrimp on it. No weight, no lures, nothing. And I tossed it in the Folly River, which is not a river, it's more of an estuary. And immediately, redfish. We had a big fish fry that night. So the kids know more than I do. They're smarter than me.
Keep it simple.
Keep it simple. Now, but the guy was fishing with lures, and he was catching redfish. Mm-hmm. And I couldn't do it. But when I put bait on a hook, they ate it, no problem.
Mm-hmm.
So why would
you were using the same lures as the other guy.
Yes. In fact, during low tide, he was fishing right over an oyster bed. I went on that oyster bed and I took his lures that he had lost throughout the last couple of days and collected them because they were sitting in the oysters because they break off. So I was using his lures that he bought and couldn't pay the fish to bite them.
But his were, and you were fishing in a close-ish area.
The exact same spot. Mm-hmm. Yeah, he had a different angle. At the
same time?
No, but he was on a dock and I was fishing from shore.
Well, that's not the same spot then.
Well, but the spot was the same. Like if you cast to the spot, it was the same piece of water. Maybe because he was casting into shallow water and reeling into deep water, and I was casting into deep water. Are you letting him
sit there, or are you like reeling it back?
Well, with a lure, you reel it back. You make it dance like a little puppet.
Well, you're dancing the wrong way.
That's clearly what happened. But they didn't seem to care. Once it was meat on the hook, they just said, "There's food. I'm going to eat that meat."
I mean, I get that though.
Yeah. Right? Yeah. To me, that makes more. I mean, that's why anglers like me are cheaters, and we use worms sometimes because we just want to catch fish sometimes. I guess meat always wins. It did, and we caught some cool fish too. We had oyster toadfish were caught.
Oh, cool!
Which are really cool, grumpy-looking, ugly fish, and they've got like fingers almost on their fins, and they kind of feel around for food. And we caught what's that fish with the human teeth?
Sheep's head?
Sheep's head, too, yeah. And those were so cool.
Can't believe I thought of that off the top of my head.
I can believe it, Doc. That's why you're here. So I guess I didn't really need your advice. I just want to make sure people know that sometimes trust the kids on their fishing. Sometimes they know more than we do.
Well, he's from around there, too, right? So
yeah, he fishes there every single day. COVID or not, he's going fishing. So... Yeah. But so, Doc, I got to get out of here. So we have to set this interview for Rachel. How do you know Rachel?
So she got her PhD at KU, University of Kansas. And now she is my newest colleague here at the university.
That's cool. That's exciting. And she's a complete nerd just like you are. So the whole conversation is really good. And that is coming up right now. So let's get into it.
Awesome.
Hey fish nerds, this is Doc Martin. I've got a really exciting guest for you today. I'm excited to bring her on here. We're going to be talking about river food webs and how they change over time. And so I will let her introduce herself.
Well, thank you. I'm Rachel Bowes, and I'm an assistant professor here at Emporia State University. And as Erica mentioned, my main research focus is on food webs in running water typically, and how they change through time.
Awesome. So how did you get to working with fish and food webs?
Yeah, great question. As most people's research trajectories, it was not a straight line by any means. It was more of a meandering path of that didn't work and I really don't like that. And so my research path kind of started in undergrad, and my first project was on plant physiology, and all my plants died, like every single one. And so the professor was like, maybe this isn't for you. And so that was my first experience with research, and so I decided I did not want to work with plants. And then the rest of my research experiences throughout my undergrad were just dabbling in lots of different things. I tried developmental biology, but most often I came back to fish. So I would study different questions, but they would all be involving fish. And so I did some studies with looking at major histocompatibility complexes and fish mate choice.
And what does that mean?
Yes.
Could you define that for us?
Absolutely. So it's part of your innate immune system. So just part of your genetic makeup. How well are you able to deal with new pathogens and diseases? And the really cool thing about MHC, or major histocompatibility complex alleles, are that they aromatize, and they're part of your natural scent, your pheromones. So why you as a human think some people smell good and why some people don't smell good to you. And it has to do with those aromatizing, and you as a human prefer somebody with more dissimilar MHC alleles than you, because your offspring then would have more diversity in their immune system, so be able to handle immune and new diseases better than you alone and your MHC alleles. So, and it's the same is true for fish, it turns out. So big, bright, and bold is really cool and beautiful in the fish world, but sometimes females don't choose the big, bright, bold male. And so that kind of led us to think, why, like, you have this really beautiful male here, why would you choose to associate with this scrawny male over here? And it turns out that it could be linked to his more dissimilar MHC alleles. So throughout my research career, I kept coming back to fish, but I did not like studying one fish species forever. I'm kind of ADD, so that's kind of how I ended up in the field of ecologies, because I like studying everything and how everything interacts with everything else. So that kind of led me to the field of ecology. And then how I kind of stumbled more along food webs, and specifically how we measure food webs using stable isotope analysis, I thought of it mostly as detective work. I can go into an ecosystem, for instance, like a river, like we'll talk about today, and I can see how organisms interact with each other and then how that's influenced by changes in their environment. And I just think it is fascinating and so exciting to see how like one little piece of this puzzle might change, and it has this cascading effect on everything else in the whole system.
Awesome. So you're in good company about doing lots of different things.
Yeah.
The fish nerds know about me very well. So what are stable isotopes? Let's start with that. What does that mean, and how do you detect them, and how does that work?
Great question. So stable isotopes are every single element on the periodic table there could be multiple versions of it. So the same element might exist in a number of different forms, if you will. And this is based on the number of neutrons in its nucleus. So for instance, if we each had an apple, and we cut the apple in half, and yours had 14 seeds in the center of it, and mine had 15 seeds in the center of it, it doesn't change the fact that it's an apple. It's still an apple, and it might look almost identical on the outside, but only the number of the neutrons, or in this case, the seeds of the apple, is different in the center. So that's the same is true for many forms of isotopes on the periodic table. So we can use isotopes in the ratio of the ones that have an extra neutron or seed in the center of its nucleus versus ones that are missing that extra neutron in its nucleus. And we can compare the heavy, the ones that have the extra neutron, to the light, the ones that are missing that extra neutron, and see how it changes with things in like diet. Isotopes can also change geographically, so we can use different isotopes of different elements to determine groundwater signatures, for instance. We can also use isotopes to look at growth and where in a habitat organisms might be living. And how I use it is to look at specifically carbon and nitrogen and look at how those change with changes in diet.
And so are these naturally occurring, or is it something you put into the system?
Great question. So they are naturally occurring. They are ubiquitous in the environment, and how they change depends on your biogeochemistry. So for instance, with carbon, you are what you eat. So if you eat a lot of corn chips, you are literally made of corn chips. If you drink a lot of soda, that's what builds up your tissues and what you are made of. And so you absolutely are what you eat. So I can take a sample of your hair tissue, for instance, and run a chemical assay on it and determine what proportion of carbon, the heavy to light, is in your tissues, and to determine from that what you're getting your carbon from. So what are you eating? Because you are what you eat. And then I can use nitrogen to determine how high on the food web are you eating. So for instance, I'm a vegetarian. So I eat generally plant materials and I don't necessarily eat a lot of other animal tissues. So I'm incorporating those plant tissues into my own tissues. In terms of nitrogen, you are what you eat plus a little bit. So we have a propensity, just biochemically, to retain the heavy version of the nitrogen isotopes. And I kind of think of it as like kids jumping on a trampoline. So nitrogen, when it has that extra neutron in its nucleus, has slightly stronger bonds it makes with hydrogen atoms. So they break just a little more difficultly. So all of your molecules in your body are always wiggling and jiggling and getting down and funky with it. And there's constantly reorganizing their hydrogen bonds. So they're constantly breaking and reforming and breaking and reforming. And the heavy nitrogen does that a little less. So you can think of it as like the really big kid on a trampoline. And so when they're all jumping up and down on a trampoline, you have all these lighter nitrogen atoms, the nitrogen 14 atoms that are jumping up and down. And then all of a sudden, a bigger, heavier nitrogen 15 gets on the trampoline and starts jumping up and down. Well, who is going to fall off the trampoline first? It's going to be one of those lighter nitrogen bonds that's going to be more easily broken. It's going to be one of those lighter kids that's going to fly off because the heavy nitrogen is jumping up and down, and he is going to stay in the center of the trampoline. And so we can use that then to determine how high on the trophic level you're eating. So if I'm going to preferentially retain the heavy nitrogen isotopes in my own tissues, so I'm going to eat some ratio of nitrogen, heavy to light nitrogen ratio in my food. And since I'm a vegetarian, I'm going to get it from some kind of plant material. And then if something were, I'm going to incorporate that into my own tissues and preferentially retain heavy ones and excrete the lighter. If something were to then come and eat me, it would incorporate my nitrogen signature, which is already has more heavy nitrogen isotopes in it, just via the fact that I retained those heavy ones in my own tissues. So then an organism's going to come along and eat me and incorporate that into their own tissues, preferentially retaining the heavy isotopes and excreting the lighter, and it's going to be increased even more in that heavy nitrogen isotope value.
And I'm going to guess that as you go up in trophic level, there's a predictable amount of the ratio change.
Exactly.
Yep. So that's essentially what you're doing then. So you can determine what an organism is eating because you understand the ratio differences. So if you know the ratio of all the food choices and the ratio of the thing eating the food, then you can kind of pinpoint, okay, well, is it eating a lot of chips? Is it eating a lot of grasses and carrots? Is it eating a lot of cheeseburgers in paradise, right? So what's happening there based on ratio comparisons?
Absolutely.
Awesome. And so you looked at this really thoroughly in the upper Mississippi and the lower Ohio River?
Yes.
Yeah, and so you had
just a couple little
streams right in the middle of America. And so your question for the study that we're talking about, it's for the nerds that are interested. The title of the paper is Reweaving River Food Webs Through Time. It was published in 2019 in Freshwater Biology. So if you want to go look that up and read the real thing, you can and should. And your interest was really how do dams change those food webs? So before we get into that, why would a dam change a food web?
Yeah, great question. So normally rivers flow and organisms that live within a river can move freely throughout the river system. For instance, the fish can easily swim up and downstream depending on their swimming ability. Dams stabilize discharge patterns, and they're going to change that natural flow pattern. So in rivers, we have natural helical cyclical flow, And our dam is basically going to stop that natural flow movement throughout a river. And probably the most obvious is it's going to stop any fish from being able to travel freely within the river system. So it has wide and varied impacts on river ecosystems in general. Also, a dam is going to stop any sediment flow that's going to be occurring. So it's going to create this slow reservoir, slow moving water called the reservoir behind it. And then it's going to have fast, cold water that's going to release from the bottom of the dam below the dam. So it's going to have wide and varied impacts on the entire ecosystem. And as you might guess, and as I alluded to before, when we change something in an environment, it's going to have some kind of cascading effects on the organisms that interact with that environment. And so we predicted that it's probably going to have some kind of impact on their food webs. And honestly, we weren't sure what we were going to find, especially this study looked at about 100 years in time. And so we weren't really sure what we were going to find. So it was kind of a let's try and see how things have changed.
Yeah, and there's different kinds of dams too. So
Yes.
In your study, you cited that there a lot of the studies have been on really big dams. So if it's a bigger thing, it probably has bigger impacts. And so you took it a different direction and said, hey, what about these middle of the road dams that aren't obviously really big, but they are still dams. So they do have effects. Do we still see that similar large effect? Is it similar effects just on a smaller scale? Or is there some weird mixture of things that it's affected here, but not here just because of that inter-range size where it's not that large extreme? Is that accurate?
Exactly.
All right. And so you looked at 70 years of data, and so you worked with a lot of museums in the Midwest.
Yes.
And so how do you get museums to say, sure, take my fish, and then you destroy them for the isotope samples, right?
Well, a small portion of them, yes.
Just a little bit.
So we don't need very much to do isotope analysis, which is one of the good things. But we do need some tissue that we're going to do the chemical assay on. And basically it's a gas chromatography mass spectrometer, and we're going to combust the sample. So yes, we do destroy a bit of the sample in the process. Yes, museums. Most people think of museums as when you go into like the Natural History Museum and you see all the beautiful displays and all the bright colors and the cool information and that one big skeleton of that dinosaur. And most people don't realize that museums are a lot more than what you actually see as a patron or as a visitor to a museum. Most museums have an open display for public, but then either in the basement or in an adjoining building, they have catalogs and catalogs of just specimens and organisms and data that they've collected over hundreds of years. So many times a scientist will be really interested in one organism and they'll go collect that for the entirety of their career. So we'll have like 50 years of them going out every year and collecting, some representative samples of this organism or this species. And then the museum will then catalog all that away in jars or filing cabinets or mounted specimens down in the basement. And so that's the part of the museum that most people don't necessarily know is there. And because that takes up a lot of space, and museums are interested in people using those specimens that are there. They're there for a reason, and they're for research purposes typically. They're to catalog the diversity of life through time so that we know what was there and we don't lose that information. But then it's also for researchers to use. And so that's exactly what I did. I literally knocked on doors and called them up. I went to approximately 8 museums throughout the Midwest and just asked, hey, can I take, and in this instance, it was just a tiny muscle tissue sample from their back or a fin clip, and just said, can I take a teeny tiny piece of one of your fish in your jars?
And so I don't know if you've read The Feather Thief,
No, I haven't.
Okay, so our fish nerds, last year, our book club read The Feather Thief. And so this is about a college person who ended up stealing a bunch of old feathers from a museum collection because he thought, well, they're just stored back there doing nothing and no one gets to enjoy them. So I'm going to break in and steal them to tie flies. And so it was a big, huge thing. And so we read a book about that. But part of the book that our fellow nerds might have read if they were joining the book club was that what is the purpose of those storage units? And they're just cataloged back there collecting dust and no one's using them. But here we are talking about it again is, yes, they are using those. And I think we had Dr. Hoellen a while ago talking about how similar museum samples were used to do microplastic assessments so we could actually see when those entered the environments. And that's a question back when we were collecting those fish in the 40s, 50s, 60s, we didn't even know to ask. And so I think this is another fantastic example of the value of museum collections where you can retroactively say, hey, now that we have all these, here's a question that we could ask that we just 50, 60 years ago, we didn't think we could. And so that's awesome. I always love museums. They're good things to have.
Yeah. And NSF, the National Science Foundation, hasn't funded my time machine yet. So this is the next best thing.
That's right. Until we have time machines, we have to have museums and all of their awesome collections, even though it feels to some people maybe they're collecting dust.
Yeah.
But also those public displays, a lot of those are interchanged, right? So you can bring some things out and put some things back, and that way the museum isn't always the same. So mix it up and do new stuff. After that tangent, so you took museum samples that were taken from the upper Mississippi or the lower Ohio River throughout this 70-ish year period, and dams were put in the U.S. typically between about 1940 to 1960, with 1950 being the intense dam building extravaganza in the United States.
Especially on the Mississippi.
Especially on the Mississippi, yep. And so you just wanted to know, well, how did they change? And so let's see. You use certain fish species. So did you select fish species based on availability and kind of completeness of collection?
Yes, that was definitely part of it. We wanted to have the same species through time. So we tried to target species that we knew would be there in the very beginning in the 1930s and 1910s, all the way through the 1990s. So there were certain species that we targeted that way. And then the other thing that we targeted were what we call invertebrate and piscivorous fish species.
And can you define those words for us?
Yeah, so invertebrate meaning fish that eat invertebrates, and piscivorous meaning fish that eat fish. So we tried to target the top, biggest predators in the system because we figured if they changed, likely everything underneath of them was changing.
There's some kind of trophic cascade happening, that big change that you've been talking about really since we started this conversation. And those larger organisms have an exacerbated response because of that change in ratio.
Absolutely.
And so you have, how many fish species did you end up using? About six or seven?
For each of the rivers, yes. And the two rivers, we wanted to see if there was a difference between the two rivers also. So we wanted to know not only how dams change food webs in rivers over the long term, but do they change them at the same way and at the same rate? And so that's why we kind of chose the two rivers that we did. Obviously, the Mississippi is one of the largest rivers in the world, but definitely in the United States, and it has a giant watershed. And because it's so big, it has a lot of museum samples. So a lot of people have gone and fished and collected those fish and put them in museums. And similar with the Ohio River, another huge river that they collected specimens through extensively through time. And so it changes a little bit between the two rivers, what species we collected. But in general, we tried to look at between 6 and 9 of the same species through time in each of those rivers.
So you got the museum samples, you did the analysis for isotopes. What did you find?
Yes, well, things have changed, is the short answer. The Mississippi and Ohio actually changed differently than, well, what we thought and also each other. So what we found in the Mississippi River is that it changed drastically over time with the addition of dams and levees. So we put on navigation levees and dams so that we can get boats up and down the Mississippi without having the river all of a sudden change. So before we put dams and levees on, the Mississippi meandered across its landscape. So the river never stayed in one spot. It's like the Pocahontas song, you can't step in the same river twice. But that's absolutely true with all rivers, but no better example than the Mississippi before. Because it could change from one town to another town, if you want to think of it that way. It would change by miles. Like, it would be here one day, and then all of a sudden the river's not there anymore. It's a mile away. So it would just meander over the landscape and change its banks all the time. It would flood and it would recede. And so we as humans don't like that at all. And so we put banks on it and we put on dams so that it stays in the same place. And by doing that, as I mentioned before, dams have a wide and varied impact on river ecosystems. So we've changed not only the fact that it's not going to move on the landscape anymore, but now we've put up big reservoirs and we've put up levees and we've basically made the river into a series of stairs so that we can navigate it and it won't move. But that changes everything in the ecosystem itself. So we've created now a slightly complex channel that moved around to stable channel banks, but we've created these huge lake-like systems with a bunch of islands and now these smaller streams that are budding off of it. And then, so we've changed the entire landscape of the Mississippi River. And as you might expect, that changed all the food web dynamics within the river too. So as I talk about in the paper, we see that this increase in complexity of the actual system itself has actually changed the food web to be slightly higher trophic positions for those top predators and change in reliance of the different food sources, that the carbon, if you will, the corn chips versus the wheat flour pasta. We've changed reliance on those different kinds of sources in this system as well.
And so let's start with the Mississippi first. So the big shift there, the fishes became more piscivorous?
Well, they started eating higher on the food web, yes. Whether that be that their food sources that the big fish were eating on were no longer there, and so they had to change to something else is probably more likely. So the fact that the fish that eat fish are still going to eat fish, but maybe they have to eat a different kind of fish.
And so what about your invertebrate fishes?
Yes, those also changed. They had a less drastic change than our piscivorous fish species, but they also increased in trophic position. So yes, in that case, maybe those fish that were eating invertebrates that lived in the bottom, for instance, they had to switch to eating some smaller fish then too.
So you're just generally seeing this shift from a lower trophic position to a slightly higher trophic position, but not anything too crazy, right? They're still generally eating the things that they eat. It's just maybe more of one other source.
Yes, and what we can say about that is that we see this constriction. So all the fish are now going to be eating more similarly to each other, which means that we've taken away some of the diversity in the foods that they might have been eating.
And what problems can that cause?
Yes, well, what if if all the organisms are eating really similarly and that food goes away, what happens to everybody else? Probably not the greatest scenario there. So that can have all sorts of influences on how organisms can adapt to ever-changing environments. Because just because we added dams doesn't mean that now we're done changing Mississippi.
Right. And so you said you found opposite or different effects, I guess. So what did the Ohio River do then?
Yeah, great question. So the Ohio River had basically exactly the opposite effect. So the Ohio River is a different beast than the Mississippi River. Before we put impoundments on the Ohio River, it was a very straight river, a single channel, and it had deep banks. It was highly what we call constricted, meaning that unlike the Mississippi, it's not going to move around the landscape very much.
And so that's a really big difference. So pre-dam, the Mississippi is highly mobile, lots of grades, where pre-dam, the Ohio was already constricted. So your starting point between these two is very, very different.
Exactly. And when we put dams on the Ohio, it really didn't change things drastically as it did in the Mississippi, at least on the overall landscape level. We did add dams that made those pools behind the dams, the reservoirs, and those are much deeper on the Ohio River than they were, for instance, on the Mississippi, because the Ohio River is just deeper than the Mississippi. So those pools are going to be deeper, and that is what we theorized is what caused some of our differences that we saw in the Ohio River. So those deeper pools means that light can't get all the way to the bottom like it used to. So anything that used to grow on the bottom of the Ohio can't anymore. And so fish and the fish's food that might have eaten that source can no longer feed on that. So they're either going to disappear or they're going to have to change strategies. And that's kind of what we see here, is that overall we have a decrease in trophic position on the Ohio River, which is exactly the opposite that we saw in the Mississippi. So the Mississippi, we added some complexity, if you might consider, we added some complexity in the Mississippi River when we added dams. So we changed the entire landscape of the river, and we added more habitat basically by creating those dams. We created giant reservoirs that were huge, wide, shallow ponds. And in the Ohio River, we did exactly the opposite. We took away a whole level of food sources that could have been available, that benthic algae, the things that grow on the bottom of the river. We basically just took that away and didn't give them anything else. And so that's exactly how, and the fish species responded to that disappearance of that food source, and we see this shift down in trophic position of the fish.
And so when you say increased complexity in the Mississippi River, do you think that other people might be a little bit, so maybe we should add dams into meandering streams to increase complexity? How do you feel about that?
Oh, yes, well, I mean, we might have added complexity in a sense, but we took away a lot more than we added, let's put it that way. And because we did see, maybe we saw an increase in trophic position, but we saw a constriction. And so all the fish that we measured are now going to be more overlapping than they were before. And so maybe, yes, we increased some food sources available to certain species, but we certainly eliminated many others and many opportunities for others. So those sources now no longer exist there. And so if we were going to change it further, we're going to see more and more species overlapping and overlapping. In ecology, when you have too much overlap, and if I'm going to eat exactly what you eat, and all of a sudden now there's half as much of that food, what are we going to do?
We're going to fight about it.
We're going to fight about it. It's going to get ugly.
Yeah, I'm a fighter, so you better watch that.
I'm a dyer.
And so I guess what are the main conclusions from this? Do you have recommendations? Do we need to know more? I'm sure there's more questions. So what do you envision for the future of this kind of research?
Yeah, well, the amazing thing is that we have all these museum specimens, and so the amount of questions we could ask is ad infinitum. And the potential to use stable isotopes to look at how food webs have changed over time, and not even just with dams, but with climate changes, with the increase in human population, with changes in agriculture and changes in land use. The questions we can ask about how things have changed over time can go on ad infinitum. And the best part about that is that if we're thinking, how did we get here, and can we go back? We have some kind of a benchmark now to say, this is what it used to look like. How can we make it look like that again?
And do you think that would be the ultimate goal, is to try to go back to how it was?
Possibly with some systems. And so the main takeaway, at least from our study, is that dams have an impact. They might not have the same impact across ecosystems, which is why it might be really useful to look at back in time and say, what did the system used to look like? And if, for instance, like these two examples, we saw much more spread in the species, so they weren't all eating exactly the same things, how can we get that diversity and, in turn, hopefully stability, so that we can have these species for a long time?
And there's some good evidence that diversification kind of begets stability.
Exactly.
And so there's a lot of good evidence that says, hey, if we diversify, if we're not all fighting over the same thing, we as the diverse organisms that exist are more likely to be able to continue to exist.
Exactly.
And so do you think this kind of research could be used to justify maybe pinpointing certain dams that should be removed?
Oh, definitely. Mm-hmm. Or at least showing how, if there's dams that have more of an impact, for instance, maybe there could be some mediations at least put in effect. A lot of times, if we, for instance, put up an impoundment and there can be no fish movement above and below, it might just be really so costly to move fish around for angling purposes or for the health of an ecosystem. Taking out the dam might be more economically feasible than keeping it in the first place. And so a lot of times we can look at how much of an impact is this dam having on the organisms in there, and is it worth it in the long run?
Yeah, because it turns out that we spend a lot of money to put the dams in, and then it turns out we continue to spend money to make that system still work.
Yep.
And so it might be worth it to why don't we just spend a little bit more money, get the dam out of there, and let the river do what it needs to do.
Exactly.
Is there anything else that you want to talk about, or any words of wisdom about this kind of research that you'd like to share?
I just think that isotopes are the coolest thing since sliced bread, and that the applications for their use in not only ecology but in science are so varied and fascinating. We use them not only, like in this paper, to look at carbon and nitrogen and track food webs, but we can use them to look at where fish live in a lake habitat, like do they live near the shore, or do they live in the bottom or in the open water. We use them to track, even find missing persons. We can use groundwater signatures to look at this missing person that is in the U.S. that doesn't speak English and doesn't know where they're from. We can figure out where, almost to the kilometer, where they actually came from because of the water that they drank. So the number of things that we can do with isotopes is so cool, and it's like detective work. And I love the fact that we can, without having a time machine, look into the past and see exactly what things used to look like and what they look like now, and maybe what we can do to make it more like how it used to be.
Awesome. And then if the fish nerds want to know more about your work or contact you, is there anywhere that they can find your research or chat with you on the internet?
Absolutely. I do have a website, and it's REBOWESECOLOGY, so rebowsecology.com. That's my website, and I also have a Twitter, and it's @EcologyRachel, RACHEL, is my Twitter handle, and you can definitely check me out on those places. On my website, I kind of do updates about different projects that I'm working on, and like try and keep it updated so that people can follow it. And then there's always opportunities if people are interested in doing research or interested in learning more about this. I have lots of projects that I work on, and I'm so excited to talk about it and to get people involved. So reach out to me either through my website or through Twitter, and happy to talk more about isotopes anytime.
Awesome. Well, thank you so much, Dr. Bose. It was great to have you here, and I'm sure the fish nerds enjoyed learning all about isotopes, because I don't think we've heard this before, so it'll be a lot of fun new information for people to think about on their commute to or from work. Great.
Thank you.
Well, thanks, Doc. That was a great interview. Thank you so much for bringing that to us. I've got some musical stuff from you that I still haven't shared with most of our audience
Oh,
yet.
God, you don't have to. Those are terrible.
They're so much fun, but maybe I'll give a little taste here and there over the next few episodes. And a little housekeeping, Fish Nerds fans. I've not put a lot of podcasts out in the last 6 weeks. I am pushing forward, going to keep making the show. But I work daily now on the radio. I'm talking 6 hours a day. So sometimes I walk by my studio and don't feel like recording. But I've been hassled a lot of emails, a lot of texts, a lot of Facebook messages. Where are you, Clay? Are you okay? I'm okay. And Doc pushed me back into the studio, which I was happy to do. And I forgot how much I enjoy making these shows.
Yay.
So
it's fun, right?
It is so much fun.
Sometimes you need to take a break.
Yeah. All right. So don't forget, go to the show notes, grab that link, sign up to be part of Doc Martin's Citizen Science Project on Microplastics. Get that done. And Doc, thanks for coming on the podcast.
Yep. Thanks for having me, Clay. It's always a pleasure.
Now I'm going to do the big finish. So that's it. You listen to a bunch of fish nerds when you should have been fishing. Big thanks to Doc Martin for coming on the show today. Thanks to Rachel Bose. Thank you to John King for the Christmas package. And thanks to COVID John for teaching me how to not catch redfish in South Carolina. A lot of fun. So until next time, follow the code of the fish nerds. Do you remember the code of the fish nerds?
Spawn early and often.
Right. Never trust a free lunch with strings attached. And swim against the current.
I was close. Go against the current every chance.
Any chance you get. That's it. You made a podcast.
Whether you're fly fishing in a stream, getting those ankles wet, or deep in the ocean, casting nets, fish nerds. Fish nerds. Fish nerds. It's a podcast.
Just for the halibut!
Fried in a basket or broiled in a pan. Eat it raw like you're in Siam. Fish nerds. Fish nerds. Fish nerds. It's a podcast.